This paper is related to the tropical Pacific decadal variability. When we talk about Pacific decadal variability or tropical Pacific decadal variability, we always mention these off-equatorial connections to the equatorial connections and the feedbacks. So this is a more specific focus on the oceanic role, the subduction of subsurface temperature anomalies in the tropical, coming from off-equatorial regions into the tropical regions, and of course that takes time because ocean moves slowly, and the issue has been whether the mean circulation brings temperature anomalies, in which case you have to wonder how they will survive this long journey. We talked about salinity compensated temperature anomalies, spiciness anomalies, which theoretically can survive, and they have to take a convoluted route because the ITCZ in the northern hemisphere is a potential vorticity barrier, so you have to go around it and you have to come through the western boundary region and so on. And whether the mean temperature anomalies are affected by the circulation, meridional circulation anomalies like the subtropical cell anomalies and so on. So let's see what this paper has to say. It says a key role of off-equatorial subsurface temperature anomalies in tropical Pacific decadal variability. So from the title you know that they are saying off-equatorial subsurface anomalies are important for tropical Pacific decadal variability, which is the topic we just discussed. We demonstrate the key role of off-equatorial subsurface temperature anomalies in driving the phase transition of the tropical Pacific decadal variability using observation and model experiments. During the positive phase of the TPDV, anomalous atmospheric responses in the off-equatorial northwestern Pacific induce positive Ekman pumping. The resulting negative subsurface temperature anomaly generated then propagates along the north equatorial countercurrent pathway towards the central basin, causing a sign reversal of the equatorial sea surface temperature anomalies around 3 years later. So it's a low frequency mode. Moreover, the positive phase of TPDV possibly changes the state of the Kuroshio extension through the tropical extratropical interactions, which subsequently projects onto the footprint of the Pacific meridional mode, thereby amplifying subsurface produced disturbance 0 to 12 months before the cold peak phase. The cold phase is completely established after 5 years. Similarly, the same dynamic applies to the reverse phase, leading to a preferred decadal oscillation driven by off-equatorial subsurface temperature anomalies and extratropical tropical ocean atmosphere interactions. Sounds complicated, but basically off-equatorial processes are producing a subsurface temperature anomaly. Ekman pumping, as you know, wind stress curl pumps the isotherms and the thermocline up and down, which can generate a subsurface temperature anomaly, which can propagate into the tropical region and transition the phase, and then that translates into ocean atmosphere interactions, atmospheric response in the tropics, which then interacts with the off-equatorial Kuroshio extension region, and then you get the next cycle. Kind of an argument that is then found in the observations. Hypothesis is developed, and then model experiments are done to test the hypothesis, and they argue that it does work, right? Let's read. The text is long, but it nicely summarizes the basic conundrums that remain that we are trying to address here. Decadal scale sea surface temperature variability in the tropical Pacific has long been recognized as an important component of the global climate system. We have already talked about this in multiple podcasts. And they trigger tremendous extreme weather events globally, such as droughts and flooding. Tropical Pacific decadal variability, I will call it TPDV like them now on, is generally defined as variability longer than the dominant 2 to 7 year time scales of El Nino Southern Oscillation obtained by an 8-year low pass filtering or 8 to 40 year band pass filtering SST in the tropical Pacific. The spatial pattern of TPDV derived by regression by the regression map is characterized by anomalies of one sign covering the equator and extending northeastward and southeastward toward the extratropics, combined with anomalies of the opposite sign in the central extratropics of both hemispheres. We have already seen this, we'll see it again, and this resembles the pattern associated with the interdecadal Pacific Oscillation as well as ENSO. So ENSO has a slightly narrower pattern, is broader, and all kinds of details are there. So when you have a spatial pattern and a time scale, you are always looking for what is selecting these spatial patterns and the time scales, right? However, TPDV exhibits a wider meridional extent and shows stronger variability in the tropics than in the extratropics. Recent studies have also identified that TPDV manifests the largest loadings in the equatorial, central and northeastern Pacific, bearing resemblance to the central Pacific El Nino and the Pacific meridional mode patterns. So we are saying many technical terms. Central Pacific El Nino as opposed to the canonical El Nino or the Eastern Pacific El Nino or the cold tongue El Nino tends to be, colder or warmer in the eastern side based on El Nino or La Nina, even though La Nina doesn't have so many flavors like El Nino does. So El Nino sometimes warms around the dateline, which is referred to as the Central Pacific El Nino, and then there is a lot of debate about whether that's a distinct mode or not, because the so-called meridional mode, which talks about the extratropical SSTs, tropical winds, and an interaction proposed by Weimont, Chiang, and then looked at by many others, basically looks somewhat like the Central Pacific El Nino, so maybe it's not independent, but then Ping Chang and others make an argument that the meridional mode actually induces westerly wind bursts in the tropical Pacific on the western side west of the dateline, which then triggers El Nino, so every El Nino is associated with this mode, and so on and so forth. That's a separate argument, but they are not independent of each other. Okay. In addition, some studies suggested that TPDV exhibits a prominent periodicity of around 11 years, mainly observed after 1950. Therefore, our focus will be specifically on the TPDV at this time scale range, 11 years range. The origin of TPDV, however, remains unclear. Since the TPDV and ENSO share a similar structure and major episodes of decadal climate variability are well captured by the relative number of El Nino and La Nina events, TPDV therefore is merely regarded as the long-term linear average of the ENSO cycle, or the residual signal modulated by the nonlinearity of ENSO. So basically, El Nino and La Nina patterns are not exactly the same when you superpose them. ENSO is El Nino Southern Oscillation, has a warm phase, cold phase, El Nino, La Nina. So if you have a decade of El Ninos and La Ninas, a low frequency rectification can appear to look like what we call TPDV. This was originally proposed by Keith Rogers, Mojib Latif, and one more person that I forget. This implies that TPDV may largely originate in the tropical Pacific. However, the wintertime stochastic forcings in the extratropical North and South Pacific have been put forward as the primary driver of TPDV. Specifically, the tropical ocean slowly integrates the seasonal development of these remote forcings in combination with the positive feedbacks such as zonal advective and thermocline feedbacks, which I won't go into details, but they happen in the tropics and it's discussed elsewhere, you can look up. So these are argued to give rise to the TPDV. Okay, so integration or slow integration by the ocean, which basically is a slow component of the climate system, can give us TPDV with these zonal advective and thermocline feedback. We've discussed Bjerknes feedback. Zonal advective feedback is basically the warm front moving, and with that a lot of coupled interactions happening. This perspective suggests that the origin of TPDV might be rooted in the extratropics. Although the proposed null hypothesis can explain the variance of decadal variability to a certain extent, it cannot account for the preferred time scale and the phase transition of the TPDV. That's critical. Due to the large oceanic heat capacity, ocean dynamics have been proposed to provide the key memory of the key memory for TPDV, the subduction of SST anomalies in the subtropical northeastern Pacific and their subsequent equatorward propagation toward the equatorial region through the subtropical tropical cell or STC has been hypothesized to determine the decadal timescale of Pacific climate variability. I've discussed this over several podcasts by now, so this is just adding more details. So off-equatorial anomalies produced, and they come in and affect, as we'll see in a minute here, affect the tropical Pacific decadal variability. However, some earlier studies suggested that these subtropical thermal anomalies decay rapidly during their propagation, and it's unlikely that the anomalies can reach the equator with sizable amplitude to make a change. In contrast, other studies indicated that compensating temperature and salinity anomalies, so spiciness anomalies, can potentially reach the tropics, albeit with much reduced amplitude. Recently, a study has identified a decadal subsurface spiciness mode in the North Pacific associated with the Aleutian Low and Pacific decadal oscillation that can propagate toward the equatorial region. Nonetheless, the degree of impact that the decadal spiciness mode has on TPDV remains largely uncertain due to the negligible amplitude observed in the tropics and the relatively short observational record. In the South Pacific, it is generally agreed that the extratropical subsurface temperature salinity anomalies can effectively propagate to the tropics on a time scale of 5 to 6 years and potentially contribute to the equatorial climate variability. There are many details there. If you don't know, you have to follow up with my other podcast, but basically there's a strong asymmetry in the northern hemisphere and southern hemisphere in terms of the connections to the deep tropical Pacific because of the ITCZ and the potential vorticity barrier it poses to the propagation of anomalies from off-equator into the equatorial region, whereas in the southern Pacific they have a more direct pathway into the deep tropics from the subtropics, and this is what is being discussed. Okay, another potential driver for TPDV is the variation in the strength of the STCs, which may determine the decadal phase transition of equatorial SST anomalies. So STCs, subtropical cells, as we already discussed, upwelling in the deep tropics, poleward transport, sinking and coming back. So it's the oceanic equivalent of the Hadley cell and approximately coincides with the Hadley cell as well in terms of the the ascent and the descent and the return. The STCs encompass subtropical subduction. Subduction is where an anomaly from the surface ducks under and gets away from the atmosphere. So the subtropical subduction, equatorward pycnocline flow, equatorial upwelling and poleward surface Ekman flow is the STC. An increase in the subsurface mass transport convergence of the STCs enhances the equatorial upwelling of subtropical colder waters, leading to cooler equatorial SST and shifting TPDV to the cold phase and vice versa. So when you observe certain modes in the observations, which are obviously statistical because you look for patterns, you do EOFs and other things, digressions, and you find a spatial scale, temporal scale, you have to explain the scale selection as well as the phase transitions, right? How you go from one phase to the other. As meridional transport variability is achieved through the oceanic adjustment associated with the propagation of Rossby waves, the preferred decadal oscillation timescale of Pacific climate can be determined by the westward propagation of wind-forced oceanic Rossby waves at specific latitudes, followed by the equatorward propagation along the western boundary as coastal trapped Kelvin waves and along the equator as Kelvin waves as well. Coastal trapped waves are also Kelvin waves because Kelvin wave needs a boundary against which it can build a pressure gradient and so on. However, the strength of the STCs is highly sensitive to both the location and magnitude of the wind forcing. In addition, TPDV can contribute to extratropical wind variability through the atmospheric bridge. Therefore, unambiguously determining the origin and preferred timescale of STC's related mechanism remains challenging. So we are finding partial answers. We know a lot of things, but a lot of things remain unknown. But This is how science works, right? Here we demonstrate that the subsurface temperature anomalies originating in the off-equatorial northwestern Pacific can account for the phase transition of TPDV using available observational and reanalysis datasets along with numerical experiments to fill in the missing understandings. Furthermore, a preferred oscillation time scale, specifically 10 to 20 years, can be established through the combined contribution of subsurface temperature anomalies and extratropical tropical ocean atmosphere interaction. So they're trying to close all the loops. So here is how the Nino 4 upper ocean decadal variability works. You can see the standard deviation with depth of the 8 to 20 year bandpass filtered temperature averaged between 5 south, 5 north. So that's the deep tropical Pacific going from the western Pacific into the eastern Pacific. So there is clearly anomaly that you can see at that time scale below the surface. So El Nino is happening mostly near the surface, even though El Nino clustering has to be associated with these as well. So if you look at the wavelength spectrum of Nino 4 SST, you can look up what these are in my other podcast. You can see that there is clearly time scales, so periods, and there is clear decadal time scale here between 8 to 16 years that spikes during certain periods. So the data is limited. That always limits your. If you have a decadal time scale that you are trying to study, ideally you would want multiple cycles or multiple realizations of that. That's where the models come in, because the observations don't give us enough cycles. This is the Nino 3 SST wavelength spectrum. So Nino 3 is in the east and Nino 4 is in the west, and you can see in the east you don't see that band here. And wavelength coherence of Nino 4 SST and subsurface temperatures, again high coherence in the decadal time period, but the coherence of the Nino 4 SST and subsurface temperature at another depth. So these are sigma potential density depths. 22 to 24.5 is shallower compared to the 24.5 to 26, because the density increases as you go down. So even at the depths there is a weaker signal. This is a stronger signal, and you can see that the near surface variability has multiple time scales as well, which we will not worry about. So this is the TPDV in blue here, clearly a decadal, multi-decadal time scale from 1950 through to 2022 or so. And these are the various other reconstructions with the SVDs, 8-year low-pass filter, and meridional transport mode. They are looking at various subsurface temperature anomalies on. Basically, when you look at subsurface temperature anomalies, you cannot simply do it similar to SSTs, because the ocean is so strongly stratified. You want to see if they are propagating along certain isopycnals or density surfaces. That's why you look at a range 22 to 24.5 and 24.5 to 26. As I said, 24.5 to 26 is deeper below the 22 to 24.5 isopycnal, and the argument is that you can clearly see a similar behavior with phase differences, and the off-equatorial subsurface temperature and TPDV have a correlation that explains the lead lag time. So TPDV lags and here TPDV leads. So the main story is still that you are looking for off-equatorial generation of subsurface temperature anomaly, its propagation into the deep tropics with these isopycnal pathways, and you are going to argue that they don't dissipate away, they are salinity compensated, so they are density anomalies, which means they can float around on isopycnals without getting totally wiped out and reach the deep tropics, and then help with the decadal variability. So this is the correlation between the Kuroshio extension and TPDV, and Pacific Meridional Mode and TPDV. Why am I being so lazy about this? Basically, I want to stick to the main message that they show with data and models that basically subsurface temperature anomalies do make it into the deep tropics, and they do play a key role, as they say. Okay, so this, sorry about that, I got cut off for some technical reason. My network is doing ups and downs. So we were looking at this figure which does some statistical analysis like correlations and multi-taper method SVD, which is some detail that I'm not going to get into, but basically these are smart people. Manu Di Lorenzo is an author on this paper as well, so I really like the guy. He's a cool guy and he's a very smart guy as well. This is about off-equatorial northwestern subsurface temperature anomalies that initiate the phase reversal of tropical Pacific decadal variability. So we are looking at the phase evolution of Pacific SST in the colors, sea level pressure in the contours that you can see on top of these, and 10-meter wind vector anomalies on decadal time scales. So the period is about 10.3 years in the MTM SVD analysis. The contour interval is something, etc. So here basically we are looking at the generation. So we are going back in months, minus 66 months. So 0 is down here. So that's when there is a phase here, but you can see the phase is positive here when you go this far back, and this is related to what's happening here, and these are subsurface SSTs. So this is kind of the basic meridional mode structure. You go from northeastern Pacific into the western dateline region of the tropical Pacific. So you go minus 42 months, minus 36 months, minus 30 months, minus 18, minus 12, minus 6, and 0 months. So you have transition from this phase to this phase, and you can see the entire thing is now negative. Wind directions are reversed, sea level pressure pattern has changed. So we are basically talking about air-sea interactions and subsurface anomalies together doing this business. And in these plots here we are looking at A to H were those, and we are looking at let me just read the whole thing. I'm being a bit too lazy maybe. So A to H phase evolution of Pacific SST, etc. that we said. The contour intervals is 0.1 HPA positive and negative with solid and dashed as usual. A and H correspond to positive and negative phases of the TPDV. So here it is the flipped signal respectively. D corresponds to the phase reversal. So A, B, C, D. So this is the transition going from positive and then beginning to grow into a negative phase. The numbers indicate the evolution of the fields in months before the peak cold phase. For example, minus 6M is 6 months before the peak of the cold phase. I to P the same as A to H, but for subsurface temperature anomalies average between 22 to 24.5 sigma theta. For clarity, positive and negative temperature anomalies are greater than greater or smaller than 0.3. So 0.3 and minus 3 degrees centigrade have been colored in red and blue. Vectors denote the mean current on the 23.5 sigma theta derived from GODAS during 1980 to 2021, which is a reanalysis product for the ocean. Only some representative current vectors are shown to avoid crowding the things. So you can now go, these are the sea surface temperatures and winds and sea level pressure. So air-sea interaction phase of the phase shift, phase transition from positive to negative. These are the corresponding anomalies, subsurface anomalies, again going from 66 months before to minus 42, minus 36. This is the transition here. Already you are in the tropics, and you can see that you are starting the positive here, which is spreading, and there is the negative. So green rectangle in I. So this is I, J, K, L, M, N, O, P. So green rectangles here are the regions defined in figure 2, which we looked at for the correlations here. Bit of a complicated figure, but you can easily see that the idea holds by combining reanalysis like GODAS and model experiments. Regressed so this is Gill response in the off-equatorial northwestern Pacific forcing subsurface temperature anomalies. Gill response is when you have a heating in the atmosphere, in the free atmosphere. It is associated with surface level convergence and divergence at the top because you have heating, and that is going to generate wind stress curl and subsurface temperature anomaly. So this is the regressed SSTA lag by subsurface temperature by 60 months. So basically saying the surface temperatures have a lagged correlation with the subsurface temperature anomaly of the equator. Oops, some noise being generated here. So this is regressed various different things here. So A to B, regressed sea level pressure and wind lead the subsurface temperature by 6 months. As we said, that's where the signal is getting generated. And regressed WSC, I forgot again what WSC is, surface wind stress curl, wind stress curl lead T by 6 months. So you can see the wind stress curl that's going to lift the isopycnals. Regressed Ekman pumping lead by 6 months. Obviously Ekman pumping is not defined on the equator because there is a F in the denominator. DJF, atmospheric response to equatorial heating. So that's the Gill response you are talking about. Horizontal response structure of the subsurface temperature. Annual atmospheric response to equatorial heating, and vertical response structure of temperature at 6 north. So that's in the potential temperature of vertical coordinate. Okay, so you can see the magnitudes of the temperature anomalies. You can see the Ekman pumping in meters per second, sea level pressure in hectopascals, again SSTA and subsurface temperatures, SSTA in degrees centigrade, wind stress curl in Newton per meter cubed, and this is the atmospheric response in equatorial heating in terms of meters. Okay, so more details of equatorial northwestern Pacific subsurface temperature anomalies propagating to the central basin via the north equatorial countercurrent pathways. So north equatorial countercurrent, as you know, so if you go here at 22.5, so you have to move deeper, 23 here, 23.5, 24. So this is near the surface, 50 to 200 meters and 50 to 300 meters, and the propagation is shown as Hausmuller diagrams going from west to east, and time going from 1960 to 2020 or so. So you can see how the propagation happens in time versus west to east, and you can see the phase transition propagating east, phase transition. So this is the idea, and corresponding sea surface temperature anomalies in the deep tropics between 5 south and 5 north, and the TPDV index here, you can clearly see the shift and the time scales that we talked about, 10.3 years. So basically it's a range of 8 to 16 years, let's say. Okay, so what does it tell you? That basically these processes are argued to work with the combination of reanalysis, which can be assumed to be data, and model experiments. So here is the atmospheric bridge working at 3 to 3.5 years, and by 2 months the wind stress curl response has produced the teleconnection, the SST, and off-equatorial SST produces equatorial wind response, which has got a fast response to winds, and you can see the corresponding wind stress curls and the phase transition happening at 2 months, and then the atmospheric so phase transition happens and then it induces an atmospheric response to that. So that looks like the Pacific meridional mode. So this takes about a year. So the phase is strengthened, transition happens, Pacific meridional mode kicks in, and that strengthens the phase, the transition phase. So the various parameters here: Ekman pumping, cold subsurface temperature, and the cold phase. So 5 years later you are going to flip the phase again. I'm just repeating and not reading much, but let's read the overall TPDV framework with phase reversal so that you just get to the processes. These figures are in there with nice titles, but since I don't have the text, I'm not reading all the text. You can go and read the text as well. Overall TPDV framework with phase reversal. The decadal oscillation framework in the tropical Pacific can be summarized as follows. Now you go back and look at the figures. Positive phase, strongest positive temperature anomalies in the Nino 4 region, which is on the western side, which is shown in the figures that we just saw. So figure 6a and 3a, I'm not going to go back. Ensemble atmospheric modeling experiments with prescribed additional 2 degrees C SST forcing further confirm that surface warming in the Nino 4 region can induce cyclonic circulation in the northwestern and southwestern Pacific. So it's a interhemispheric response respectively, leading to the corresponding positive and negative wind stress curl anomalies in the 2 to 15 degrees and 2 to 15 degree north and 15 degrees south latitude bands in both hemispheres. The resulting positive Ekman pumping that we just saw drives negative subsurface temperature with the strongest signals in the off-equatorial northwestern Pacific. This is also confirmed by the ensemble ocean modeling experiment, and TPDV associated wind fields were prescribed. So they are forcing an atmosphere with warm or cold anomaly in the deep tropical Pacific to produce the wind stress curl response off equator, then producing this, then take those winds and force an ocean to see that in fact you can produce subsurface anomaly, and then that reaches the deep tropics. The transition phase then, off-equatorial northwestern subsurface temperature anomalies gradually migrate toward the central basin along the NECC pathway, the north equatorial countercurrent. In case you don't know what that is, I have it in my basic climate courses or oceanography courses. You have winds pushing the water and piling up against the western boundary. Then you have a piled up gravity flow that, because of Coriolis, it's going to be trapped by the equator, so it can remain coherent for quite ways. In the north, just to the north of the equator, the NECC in the Pacific goes almost all the way to the east, but we just needed to bring the anomaly from the western boundary towards the dateline to start the process of feedback through air-sea interactions to the extratropics, right? As the isopycnal shoals towards the east, negative subsurface temperature anomalies are accumulated in the Nino 4 region around 3 years later. Okay, so that's what we were looking at 3 years later here. Okay. Strengthening phase. During the positive phase of TPDV, warming in the equatorial central Pacific triggers a train of atmospheric Rossby waves to induce extratropical atmospheric circulation anomalies around 3 months, driving westward propagating oceanic Rossby waves that affect the Kuroshio extension system around 2.5 to 3 years. The change of the Kuroshio extension state then induces a downstream atmospheric response. So Rossby waves going west from the northeast Pacific to the Kuroshio extension response, then sending a signal back through the atmosphere to the northeast Pacific again. Okay, so the change of the Kuroshio extension state then induces a downstream atmospheric response that projects onto the forcing pattern of the Pacific meridional mode. The PMM further strengthens the subsurface induced SST anomalies in the central equatorial Pacific 0 to 12 months before the peak of the cold phase, which was shown here in 6C. Okay, so this is not so well marked. Are there A, B, C written somewhere? Yeah, we are coming this way, so that's C, and then that's D. So yeah, so here, so warm phase, phase transition, strengthening phase, and cold phase. There we go. Okay, sorry about this. The accumulation of subsurface temperature anomalies in the Nino 4 region originated from the off-equatorial northwestern Pacific subsurface anomalies, along with the enhancement of the Kuroshio extension and thus the PMM contribution, result in the cold phase of TPDV after around 5 to 6 years. setting up a half a cycle of the decadal oscillation. The remaining opposite cycle is simply the reverse processes mentioned above in figure 6. Okay, so this is the transition from here, which is about 5 to 6 years, and then you go back. So the total cycle is basically the decadal cycle. Okay, discussion kind of long. Should I just read it? Yeah, let's just do it. Based on available observational and reanalysis products and ensemble model experiments, the study presents a modified framework of TPDV involving off-equatorial subsurface temperature anomalies and extratropical tropical ocean atmosphere interactions. The combined contribution of the off-equatorial subsurface temperature propagation and PMM eventually leads to the mature cold phase after 5 years. The center of the equatorial negative SST anomalies then forces anomalous atmospheric circulation, resulting in positive subsurface temperature anomalies in the off-equatorial western area and potentially reversing the state of the TPDV. Thus, a periodic oscillation of 10 years is achieved. So you just have to make sure to sit and look at it and make sure you understand where the anomalies are generated, where it's popping up to affect the SSTs, how the SSTs then feed back to the wind stress curl and induce Rossby waves, feedback, and then phase change. Strengthening in the middle. Impact of PMM in strengthening the TPDV during the transition state remains a subject of debate. So some hand waving is involved there in interpreting these. A recent study indicated that while the causal relationship between PMM and TPDV is apparent, the influence of PMM might have been overestimated in the previous literature. Further analysis is required to investigate the extent to which PMM contributes to the strengthening of the equatorial SST anomalies during the transition state. Another noteworthy issue concerning the decadal phase change of PMM. There is a I misread it. Another noteworthy issue concerns the decadal phase change of PMM. While KE can partially explain PMM forcing, uncertainties persist regarding whether PMM is influenced by factors within and or outside the Pacific. So is it Kuroshio extension affecting PMM in back, or is it coming from outside? This is not completely clear. While KE can partially explain PMM forcing, uncertainties persist regarding whether PMM is influenced by factors within and or outside the Pacific. Some studies indicate that the decadal PMM is primarily driven by a tripole mode pattern of SLP anomalies extending from northeastern Asia to the northeastern Pacific. Conversely, others suggest that the positive phase of the Atlantic multi-decadal oscillation can weaken the Aleutian low via atmospheric teleconnection, thereby contributing to PMM. So lots of unknowns. Further investigations are necessary to discern the fraction of decadal PMM variability driven by intrabasin factors versus interbasin factors. Moreover, it is crucial to explore how these physical processes activate the preferred decadal timescale variability of PMM. Unraveling the intricacies of the decadal phase change of the PMM extends beyond the scope of the present study and may be explored more thoroughly in our future research. Essentially, you are invoking intrabasin processes and interbasin processes, but then when forcing comes internally or externally, you have to explain how they are picking these specific modes like PMM. So why is tropics forcing a particular response in the extratropics, and so on, right? TPDV associated SST anomalies can induce extratropical anomalous wind fields generating off-equatorial Rossby waves in both the North and South Pacific. These waves then propagate westward and may potentially contribute to the phase transition of TPDV. So we've been focusing on the northern hemisphere, but we know that there is a southern hemisphere response, and the southern hemisphere pathways are faster and more open. We show the temporal evolution of SSH anomalies along a specific circuit westward along 13 north in the supplementary material, and then equatorward along the western boundary at 130 degree east, basically along Philippines, Mindanao, and down into the equator, and eastward along the equator. Most of the SSH anomalies originating west of 160 degree west appear to reach the western boundary at 13 degree north after 2 to 3 years, then follow the western boundary to reach the equatorial West Pacific and propagate eastward to the central basin along the equator at much reduced amplitude. So there is a damping involved there. Along the equator, we also observe the propagating SSH signals disconnected abruptly around 160° east, suggesting that off-equatorial Rossby waves might not be the primary contributor to the phase reversal of TPDV. So after all these discussions, there is still some unknown about what happens to the signal once it reaches to the deep tropics around 160° east. Furthermore, a recent study postulated that the robust ENSO events could potentially influence the phase transition of the TPDV. So it's not just about intra-basin, but also in the tropics itself. However, we have identified only two distinct ENSO events that could play a role in the phase transition of TPDV within the scope of our analysis: the 1965-66 El Nino and the 2007-2008 La Nina. The former may contribute to the transition from a negative to a positive phase, while the latter may have contributed to the transition from a positive to a negative phase of TPDV. Nonetheless, a more comprehensive analysis is necessary to accurately quantify the degree to which ENSO events contribute to the phase transition of TPDV. There is no reason to believe that any of these are exclusive, that only PMM is involved, only intrabasin is involved, only ENSOs are involved, only AMO is involved. They could all be acting, and the scale selection and the responses happen based on many other background conditions, right? That's always possible, that certain ENSOs can do deep tropical transition, certain ones require a PMM and the tropical extratropical ocean atmosphere interactions. Some respond to forcing from the AMO, because AMO phase transition is multi-decadal as well. So multiple time scales involved. So this is a complicated story, but I hope you get the idea that we are basically talking about the importance of generation of subsurface temperature anomalies in the ocean by the winds off the equator, that anomaly traveling to the deep tropics. Evidence for that seems solid, and yet it's not clear whether that's the final answer to the phase transition of the tropical Pacific decadal variability. Okay, so more will come, of course, and if anything new and exciting comes along, I'll add here, since anyway we are keeping this under new findings, so we can keep on adding newer findings. Okay, see you in the next topic then, which is about recycling cement, I think.